Hi, everybody. Welcome to our next round of fellows presentations. Today we have Ernest, Petro, and Leonid. Um, Ernest, you're up first, so whenever you want to get started, go right ahead.
Yeah, okay, fine. So, hello audience. My name is Ernest, and today I'm going to present you my project, the HSF Conditions Database Intelligent Caching, and my mentor is Leonid Didukh. So let's get started. Firstly, I would like to tell about HSF Conditions Database. So HSF is abbreviation of HEP Software Foundations, like a forum of people from different experiments that are collecting together to develop new stuff using their experience. And in our case, they're developing a conditions database that's already in use in Phoenix, in BNL. They had already published set of recommendations for it. And you can see the short overview of this set on the right side of your screen. So they separated client side and server side. And when you are trying to download your file of payload to the server, its file goes to the remote payload store, and the URL of this file goes to the no payload database. And we need to understand that client side and server side connected with a REST API interface. So going to the cache, we'll already have implemented cache between no payload client and remote payload store. In my project, we're going to develop intelligent caching for no payload database itself. So what about examples? Below you can see the example query of this request. So we have HTTP type of request with the API payload IVs, and we have two features as GT name and IV num. So GT name is like label of our file, and IV it's like feature of the time because of our agnostic design of the experiment of condition database of experiment. We need to develop some kind of time feature. In our case, it's interval of validity, IOV. So going to the cache, in the main parts, we have a cache style that contains URL, our main part, response, and some kind of additional information like request time, frequency, etc. When our cache is full, we have some kind of eviction policy. We evict one cell and replace it with a new one. On the right side of your screen, you can see the algorithm, how cache works. So we have new request, it goes into the cache. If it's in the cache, we get response from the cache. If not, we get response from the database. And then we update our cache. And then check if cache is full, we evict one cell. If not, algorithm done. So I would like to represent you three main strategies. It's like FIFO, LRU, and LFU. So let's start from the left side. FIFO, first in, first out. So when we have first cell as an input, it would be first as an output. It's like simplified ordered dictionary eviction policy. If we're going to talk about LRU, least recently used value, it's mean when you were not using one cell for a long term of time, we evict the cell out of the cache. And almost the same one in the LFU, least frequently used. So if we're not using our cell so frequently, we evict it out of the cache. Here where I will show you the example of our data from Phoenix. We can see these 3-4 horizontal lines. And I would like to also mention that it was like first iteration of calibrations of the experiment. And that's why they're using only 4 or 3 types of files with a 3 set of numbers of minor OV. So as a result, they have these like straight lines. That means that we don't need to use intelligent caching instead of something simple strategies. In our case, we try to use LRU strategy, and as a result, we had 99.6% shares from the cache. But we're trying to develop intelligent caching. That's why we are trying to ask another experiments for new access log files, and we really want to thank Kostin Grigoras from Alice, from Andrea Formica from Atlas, Dave Dijkstra from CMS, and Chris Finkenburg from a Sphinx that gave us their log files, access log files from the web server, and we investigate them. So after a few iterations, we understand that they're not one-to-one comparable with the HSF Conditions Database. That's why we're trying to develop our own simulated data with the basic patterns. In our case, it's just a data type simulation. When we increase our minor RV, our feature one by another due to some period of time, and simulation type of data when we're just pick random value in some kind of gap of values. So as a result, we had that set below on the screen with all these colored dots. We have here 3 campaigns running in the parallel. So we have data lake with 100 requesters with 1 second and 2 second period, and simulation like with 100 requesters and 2 second period. And then I also need to mention that we have only 100 categories, like 100 minor OVs in our dataset, and as a result, we have around 30,000 requests, like length of our dataset. Based on it, we're trying to check our classical strategies. In our case, it's LRU, LFU, and FIFO. We also checked another one, but they're not so good as this one. So you can see here that for each of these points, we run our algorithm one by another for different cache sizes. So as a result, we have information that LRU is the best one from classical strategies, but also we implement here cheat cache. That's something like optimal cache strategy that could exist in the theory. It knows all requests for all the time, and it predicts, it's count the best optimal strategy in our case. So our goal in this project to reach this level as much as possible. That's why we tried a deep learning approach. So first, our point was to predict the next value, next request, with the knowing about what request was 100 steps before. So we have 100 requests before our prediction, and as a result, we predict one value on the next step. So you can see our hidden layers with dense and LSTM, long short-term memory. And as an output, we're using probability for each of 100 minor OVs to be requested on the next step. And eviction policy based on this output, so we remove cell in the cache with the lowest probability to be requested on the next step. We can see on the right side of our screen on the plot that our result is better than LRU, but also it has its own problems. For example, its processing time. It's slow comparable to the high frequency requests that we had in the real life, and it needs additional memory for processing. But obviously, this problem can be solved and optimized in the future. But for now, we're going to another approach. It was reinforcement learning, like in Q-learn in our case, and we're using I would like to explain it shortly. It has 4 concepts. First is state space. So imagine that we have a robot in some kind of maze. We have bombs, lightnings, and the end of our maze. And state space, it's each square in which robot can be. So like indexes of all the axes where robot could exist. Action space, it's all movements that robot could make. It's like going up, left, right, down. And the reward is like reward of the action that a robot make. So for example, if robot goes right, it gets reward minus 100. And if robot somehow goes to the end, it had the reward like plus 100. And the Q table, it's like matrix, the result of all of these 3 spaces of states, actions, and reward. And we rerun all these cycles of robot going into the maze for all this time, and Q table updates until we have the optimal strategy for the robot, how to solve all this maze. We're using simplest Q-learning formula here that based on the current Q value, learning rate, reward, and discount rate. And going to our cache. In our case, we're using time-ordered dictionary cache. We're using for eviction first and last two values of the time-ordered cache, like two least recently and two most recently used values. And as a states, we're using parameterized states of the combination of features like IV, counters, and timestamps. For example, like in our case, it's in Boolean or discrete format because we're trying to reduce runtime as much as possible. Also, I need to say that, for example, difference of the timestamps shows us the actuality of the value, and difference of IV shows us backwards values. So it's important to use them. And as a result, we have a nice plot on the right side where RLU almost everywhere better than LRU, not as much, not as better than deep learning, but at least something, but with a normal runtime, like around 1 millisecond. So as a conclusion, so I'd like to say that we investigated different request logs of the condition database of Phoenix, understood that we can use LRU in this test format that they're using it for now, and it gave us result around 99.6% source from the cache. We checked another access logs from the different experiments, and we developed, we make our own simulation of the data, our own data set. We developed two intelligent caching methods for it, like supervised deep learning and reinforcement learning. And both the result is better than the LRU, but they have still window to optimize the runtime and robustness of both of these methods. So that's all. Thank you for your attention.
Thank you, Ernest. Any questions for Ernest? Your mentor was Lino. Lino, do you have any comments?
Sure, I can ask a very generic question to you, Ernest. First, thanks for the very nice talk. If you had more time to work on this project, what would your next steps be?
I think I will implement deep learning stuff into the reinforcement learning. For now, we're using just a Q table, Q values methods. But if we're going to work in the future, I think deep learning in combination with reinforcement learning could give us normal results. I hope with a high runtime. So just in the future. That's all.
Okay. Thanks.
All right. Any other questions? Nice talk, Ernest. Up next, a little change in schedule. Leonid, you want to go ahead and share your screen and we can get started?
My project was about the profiling and energy estimation of ML-based compression algorithm framework Baler using the HEP data, and my mentor is Katerina Doglioni. So I basically start with the motivation for the profiling and the improvements of energy consumption. And later I'll describe the results of the profiling training, and so during the studies I was appropriated several energy meters, and I'll show you the results and then the short summary about how it's possible to speed up the training and the inference of this framework, and also to reduce the energy cost and energy consumption. So as you know, the data in the world is growing, and this is the same way the size of DNA architecture that publish it every year is also growing, and the number of operations regarding to the training and inference is increasing. Therefore, the training procedures becomes more costly, and it consumes more electricity, more power, and emit more CO2. So the profiling is the way the really programmers use in order to indicate or inspect the most costly operation, to debug it, and also improve the software. So we use several base profiler in order to inspect the Baler framework. Also, it helps to reduce the cost of the execution of software and to reduce the CO2 emission. So our studies was regarding the Baler, its machine learning-based compression framework for scientific data, based on the autoencoder architecture, and provide currently several benchmarks using the HEP and computational fluid dynamic data. We were mostly interested in the HEP data, and it provides the interface for the compression decompression of the data, as well as inspecting the performance of the training and inference. So in our case, there were several data sets to use. I was mainly concerned on the small ones. It consists the one event is represented like 24 size vector, and it was used for compression. So each of the events were compressed with the compression rate 1.6, and later was expected. So the concerning the size of the network, it consists of the 4 encoding layers and 4 decoding layers, and the total number of the flops is 0.033 gigaflops per second, and the max is multiply addition operation, and 31 million in this case. So the basic procedures that we were tracing and inspecting is training for 1000 of epochs using the small data set, and there are a lot of sensitive features that can impact the speed of this training. Like the first of all is the batch size, but it was fixed for the most optimal value, like a 512. And the optimizer and learning rate scheduler was fixed. So we use the Adam optimizer and starting learning rate with 0.01. It was done using the LX Plus. The study was done with hardware. We had the Intel Xeon Silver CPU and Tesla T4 GPU. So if you want to look much more deeply in some settings regarding this hardware, so it's presented in this picture with a reference. So I would like to mention that we had only one GPU, so no data parallelization was studied. So let's go deeply to the training procedure and the results, how it works. So here you can see the some on the left what the activation power pattern of the picture of the activation layers, and the right plot the loss dynamics during the training. And so this is a basic procedure that we studied and measured the time and other profiling metrics and the energy related to the training. So in the end, after the training, it provides the compressed data, and here you can see the picture of distribution of some features before and after the compression. It's provided in order to check the work this framework. So here we have the PT and phi. I just put the three of them. And let's go back to some technical things. So profiling metrics, there's a whole list of the possible metrics that possible to use in order to expect training, including the program time, the hardware time, multiplier accumulate operation, floating point operation, as the total memories that were consumed, energy in joules, and power consumption in watt. So this whole metrics was expected, and for the simplest case, we used the C profiler in order to estimate the total time, total execution of this training and inspect the most costly operation. So the most expensive operation is a sampler, and the total time is like 700 seconds, and later on only all the operations that were regarding the training, the gradient optimizer are coming. So for this operation, the data loader itself and the reading and writing the data is the most expensive. This could be optimized. So here's the same plots that we got with the C profiler, but it shows the compression and decompression of this data. So later on, if you want to inspect what is the most expensive and what's the operations that could be optimized for the compression, decompression, so we find that the operation regarding the works with NumPy concatenation that takes a lot of memory and there's a lot of coping operation. Also, while the passing through the networks, it consumes not that much memory, and it's not expensive at all. So the similar thing was done for the decompression. In this case, if you can see the first line, the work with NumPy is the most expensive. So I would like to go further and describe the work that was done with energy profilers. So we expect several energy profilers. One of them is tools. Most of them are reading the information in case of if you want to get information from the GPUs, they are reading the information from NVMeL, and in case of CPU, it utilizes the information from running average power meter in case of Intel CPU. So this framework is pretty simple. It allows to read the power of the GPU and also provides a way to optimize the energy cost by running by using this formula below. So where the eta is accuracy of the model with some target metrics, and max possible power of the GPU, and TTA is the time regarding the execution, related to the execution. So in our case, we use this framework only for the reading because the framework itself, in order to optimize the GPU power level, it requires admin rights for the Intel Plus, so I didn't have it. So I use it only for the reading. So and here you can see the information about the duration of the execution of training and the GPU energy in joules related to this process. So in total, it takes like 100 minutes to produce the training, and an average 290 joules was consumed for one epoch. So there's another framework that was expected, and I find it that it's the most suitable for the practical usage, and I added it to the as a pull request to current as a closure decorator for the Baler framework in order to inspect the on the runtime the energy, time, and amount of CO2 that was emitted. So here you can see the code. It works pretty simple. As you can see, it could be converted to the closure, and it's possible to inspect on the instruction-based level the energy and the energy and power that consumed by RAM, CPU, and GPU. So here is the result of the profiling with training for 1000 of epoch. And the results are pretty similar to the what Zeus provides. And on this plot, you can see the total energy that consumed per epoch and the duration of the operation per epoch. So in order to summarize, it's possible to plot to see the total CO2 that was emitted, and as well as the duration of each of the procedure for the compression and training. And so I put these plots in the log scale in order to make it a bit comparable, because as well as the training takes much more than compression and decompression. So here you can see the similar plots, but for the energy in kilowatt hour and in joules for three of these procedures, and for each of the hardware part. So I will go further, and we started one more energy meters. It's equal to E. It's can provide also this information, but only for about the CPU and GPU devices, and recalculate the carbon emission, take into account the region emission coefficients. So in this case, the power consumption for the whole system hardware was estimated, as well as CO2 that was emitted. Okay, so while it's possible to read and estimate this all information about the time and the about the energy, power, and the CO2 that was emitted, it comes natural question how to optimize all of it. So first of all, it's possible just to optimize the power, to change the power of the hardware, so the CPU and GPU. Or another way, it's just to simply change some tunable parameters, like a batch size, and or get some hyperparameter tuning concerning not only the precision metrics, but energy and CO2, for example, and run the optimization in this way. Thirdly, so as it was shown that data loading, operation, and working with NumPy arrays is the most costly. In some procedures, it's possible to use Numba or QP in order to work with NumPy. And fourth, one of the very popular strategies for the training is use half precision or use automatic mixed precision, as it utilize less memory, and as a conclusion, it uses less energy. One also is possible ways to use the data parallel, model parallel strategies in case of distributed training, but it was not analyzed, it was not done because we didn't have the multiple devices for this. And I will show you the mixed precision training, one strategy instead of using the full precision number representation. It's possible to switch from the floating 0.32 to floating 0.16 weights during the forward pass, and then for the back propagation move to the normal precision back. So this operation can speed up the training, but it's in several studies it was shown that it's reduced the accuracy or performance of the model for a bit. So we observe the similar behavior. So the several experiments was done. One for the from the left, what you can see the normal training. The middle one is automatic mixed precision without loss scaling, and automatic mixed precision with scaling. So it's possible to reduce the total time from 100 minutes to 89 or 92 minutes, and as well to reduce the energy that is consumed for this procedure. But on the other side, the loss, the final loss point is it's a bit different that you can get in the concerning the normal training. So this strategy can be utilized, but if the precision is the first thing that matter, then it's necessary to switch to another strategies. So, and as a conclusion, let's show that we measure the time and operation-related metrics for training and inference, measures the power consumption and the CO2 emission of this training. Also, the automatic mix procedure was appropriated as a way to speed up the training procedure. So results of the experiments are stored in this repository. So, and I would like to say big thanks to Katerina Dugdovani, Alexander Ekman, and Baler collaboration for this work. Do you have any questions?
Thank you, Leonid. Any questions for Leonid? Your mentor, Katerina, is connected. Katerina, you have anything you'd like to add?
I mean, I think it was very enjoyable to work with Leonid. He always had new papers for us to read, so he's been mentoring us as well. So he's got a lot of GitHub repositories that have been students. So we'll share those whenever we have had some time to tidy up after finishing.
Okay. Any other questions? No. All right. Thank you, Leonid. Nice talk. Thank you, everybody, for coming. There'll be more soon. So, bye.
Thank you. Bye.
Thanks. Bye.